In this video, we're going to go over how to calculate head loss in multiple pipes and fittings. And as you're probably aware of what we've gone through so far, we've learned how to calculate the head loss in a single pipe, but you're rarely in an engineered system going to be dealing with a single straight piece of pipe that doesn't have a bend in it, or a T, or multiple valves, or reducers where you're changing from one size pipe to another. And so we really need to be able to calculate head loss in a more complex setup of a piping system, and that's what we're going to go over in today's class. So a single pipe system often has multiple pipes with different materials and dimensions, as well as different fittings, valves, inlets, T's, bends, elbows, each of which have a significant and specific contribution to the head loss. And we clarify these and classify them in two different forms. We call the friction losses in the pipes themselves to be major losses. And once you work some of these problems, you'll see why that is really the major contributor to the head loss in a lot of these systems, is these long runs of pipe. And pipes can be run in multiple ways, either in series or in parallel, just like a circuit, either one after the other, or all three sections or five or however it be in sections all at the same time, and then coming back together at another point. So they're connected, but they're all coming across that way. So in series, it's pretty straightforward how we do this. So if, for example, I showed two drawings here where we have a small pipe at P1 that is connected to a larger pipe in P2, or say we have same size pipe of two different materials connected, which is going to change that friction factor that we learned about in the previous videos. And so say we have copper pipe adjoining a PVC pipe, and so our friction factor is going to be different, but our velocity might be the same. Well, in series, it's pretty straightforward. We just add them up. So the total head loss is equal to the head loss of pipe 1 plus the head loss of pipe 2, all the way up to whatever end pipe we have. And so we can simply say that the head loss is equal to the summation of the different types of pipes, so the friction factor of those particular pipes times the length of those individual sections divided by the hydraulic radius of those individual sections times the velocity in those individual sections squared over 2g. And we just add it all up, and that gives us our head loss. So in series, really straightforward. When pipes are done in parallel, it's a little bit different, and it's pretty interesting how it works out. So look at the schematic here for the in parallel, and we have two pipes. You have water coming in, it splits, it goes across, it comes back together, and comes out an exit pipe. And so let's think about the conservation of energy equation between points 1 and points 2 here. And if you actually go through it, and I won't go through it here in detail, but the pressure difference between point 1 and point 2 must be the same. So if we think about our conservation of energy equation and we get rid of all the other terms, and we end up with this H sub L is equal to P1 minus P2 over gamma, what that means is that if the pressure difference across those two sections of pipe must be the same, then the head loss must be the same. So that the head loss is equal, the total head loss from 1.1 to point 2 is equal to the head loss in pipe 1, which is equal to the head loss in pipe 2, all is equal to the head loss in section N. So in parallel, it's all equal. The head loss will be equal. And the way it adjusts that is if you have pipes of different diameter or different friction factors, the only thing left to change then is the velocity in the pipes. And so since we have a Q coming in at point 1, the same Q leaving, what it means is that the flow will partition itself between the different pipes such that the pressure difference is the same. So the head loss is the same. And it'll automatically adjust. So if you just turn on the system and it starts flowing, the water or the fluid itself will adjust so that that pressure is the same at the 2 points. All right, so that's how we do it for pipes. The other types of losses that we have in a piping system are what we call minor losses, in converse to the major losses. And the way we calculate those is simply that the head loss is equal to summation over the number of fittings of a loss coefficient K sub L times the velocity squared over 2g through that fitting, where we often take the velocity through the fitting as the velocity of the incoming pipe. Okay, so the loss coefficient is actually tabulated for a lot of different types of fittings, and I've given you some examples here. For a 90-degree elbow, it ranges from 0.2 to 1.5. That really has to do with the type of material, the opening at the end of the elbow, how curved it is. Is it a sharp 90 degree or is it a nice slow bend? Gate valves have values from 0.25 to 20. Ball valves 0.05 to 200. And for valves, it really depends on how open the valve is. Is it 98% closed or is it wide open? Okay, and so when it's really closed, then the case of valve is going to be really big because it's a tiny little opening that we have to squeeze all that water through. When it's wide open, it's going to be very small because it's going to be basically the same as the interior of the pipe. And then for a T, so if we're going to split the flow and we're going to just have it T out or Y out, it can range from 0.2 to 2. And again, that has to do with, is it a straight perpendicular T or is it a Y-shaped T? Does it have some nice curvature to it? And how rapidly are we going to try to shift that momentum to a different direction is going to have a huge effect on that loss coefficient. Okay? So what we end up getting is that the total head loss is, say, for a pipe series system is equal to the summation of the head loss in the pipes, which is the first part of the right-hand side of that equation on the board, plus the coefficients of head loss due to the fittings. So friction loss, pipe fitting loss, major and minor losses, and we add them together, and that ends up being what our head loss is in some sort of piping network. So the next couple of exercises, we'll go over a couple of examples, specifically a pipes in series and a pipes in parallel example.